Alright, so to continue, the next question that we are going to ask ourselves and answer is the following. Having looked at what are all the forces that act on the vehicle and what is the output delivered by the powertrain for a given prime mover torque and selected gear ratios, the question becomes, if we are given a set of vehicle performance requirements and a base prime mover, an engine, how do we select the gear ratios? Okay. In other words, how do we match the capabilities of the powertrain with what is required by the vehicle designer as far as vehicle performance is concerned? This exercise is typically referred to as what is called as transmission matching by sum. Okay. So, what is the question that we are posing? The question is how to obtain the gear ratios of a multi-speed gearbox and the final drive to meet vehicle performance requirements. Of course, given a base engine, right. So, given a ratings of a engine, how do we essentially go about and calculate these values. Okay. In other words, we would also want to essentially figure out how do we convert like vehicle performance requirements like gradability, maximum speed requirements, etc., into some useful mathematical relationships that can be utilized to obtain first cut values of these gear ratios. Okay. So, that is the question we are asking ourselves. So, in this regard, let us consider a n speed gearbox, okay, without loss of generality. So, what is meant by n speed gearbox? There are n gears, okay, in that gearbox. So, let us consider a n speed gearbox with the corresponding gear ratios being NT1, NT2 all the way till NTN. Okay. So, we need to determine the values of NT1 through NTN. Okay. Further, we also need to calculate the gear ratio of the final drive, which is denoted by ND. So, in other words, in the process of transmission matching, we need to calculate the values of NT1, NT2 all the way till NTN and this parameter ND. The question is that like how do we go about doing this? So, let us discuss that. So, the first vehicle performance requirement that we are going to look at is what is called as gradability. And to be very specific, like we are going to discuss what is called as continuous gradability. Okay, like we will see what is the difference, between this and another form of gradability shortly. Okay. So, what is gradability? So, gradability is indicative of the maximum grade that the vehicle can climb at a given speed. Okay, so that is the notion of gradability. So if theta s max is the maximum slope angle, then gradability is defined as G, parameter G is denotes gradability. G is the tangent of theta s max. Okay, so that is the notion of gradability. Okay, so tan theta s max is gradability. Okay, fine. So typically when we want to go on a grade, right, a vehicle goes on a grade, we would want to essentially look for a choice of a gear ratio such that the vehicle travels at a constant speed. Okay. If that were the case, we are looking at what is called as continuous gradability. Okay. So the adjective continuous essentially considers a scenario where my vehicle is going on a grade but at a constant speed. Now if a vehicle is going at a constant speed on a grade, what do you think are the loads that the powertrain needs to overcome? Yesterday we identified 5 loads, right? Inertia, aerodynamic drag, grade resistance, rolling resistance and draw bar pull, right? So in our analysis for continuous gradability, what do you think are the loads which will play a dominant role? So significant loads would be the following. So do you think would inertia play a big role? No, right, because the vehicle is going at a constant speed on a slope, right. So inertia will not play a big role. The one term which is going to play an important role in gradability is grade resistance, because W sin theta s max is going to dominate all the other forces that the powertrain has to overcome. So rolling resistance would be there. Okay. Aerodynamic drag, typically as I mentioned, like for most vehicles, like it becomes reasonably important at mid and high speeds. Typically when you are going on a grade, you design for low speeds, right. So consequently it is a reasonable assumption to neglect aerodynamic drag for this particular calculation. If you want, you can include, you will see that some people will include it, some people may not. Okay. So it is a matter of choice. Okay. So as a first cut analysis in this exercise, we are not going to include, and we will also neglect draw bar pull. We are assuming that the vehicle is not basically towing any other entity. Okay. So those are the assumptions. So the significant loads that the the powertrain should overcome during climbing a grade at a constant speed are these, right. So this is at a constant speed. So there is something else called starting gradability. So what is starting gradability? Starting gradability, this as a aside, typically what happens is that like the people evaluate what is the ability of a powertrain to just start moving the vehicle when the vehicle is initially stationary on a grade. So imagine that the vehicle is kept stationary on a grade. Okay. The question that we are asking when we are dealing with starting gradability is that what is the capability of the powertrain to just start moving the vehicle up the grade from a stationary position. Then in addition to the grade resistance and rolling resistance, inertia also will play a role, right, because of course it will play a small role, but nonetheless there will be a role for inertia to play because we are starting from rest. No matter that we are starting from 0 speed and then we are going to a low speed, maybe over a longer time interval, still there is going to be some average acceleration, right, which is going to introduce that ma component, right, in the equations. So inertia will get added and the powertrain then has to overcome these 3 loads. Okay. So we are going to consider continuous gradability. This is just as an aside, because you will see that some what to say, designs may require us to deal with starting gradability. Then the only difference from the analysis that we are doing is that we need to add that ma term, that is what. And as I told you, some people will add that what to say, aerodynamic drag term. Okay. So it depends on the scenario. Okay. So for us, for the first cut analysis that we are going to do, we are going to deal with grade resistance and rolling resistance. Okay. So that is what we are going to consider. Thus, the tractive force. So in this course, if I talk about gradability, by default I am talking about continuous gradability. Okay. Let me clarify here. So the tractive force required to overcome the significant loads is W equals, not W, F, which is the tractive force. This will be grade resistance is sin theta, W sin theta S max. Okay, that is the grade resistance. Then rolling resistance is Fr times W. So these are the 2 loads or forces that the vehicle should, the powertrain should overcome, right, for continuous gradability. Now, typically what happens is that, like, we expect to engage the first gear when we are going on a maximum or the highest grade possible, for a particular vehicle design. So imagine that we are going on a mountainous terrain or a flyover. By and large, what we would do is that, like, the design is such that we want to get the maximum possible thrust, from the prime mover, and the gear should be such that the magnification of the torque which is delivered by the prime mover is also the highest. Okay, because anyway we are dealing with low speeds. So if you even recall the ideal traction hyperbola, right, when you are going at low speeds on grades, like, we want to essentially have a high force, right, because we want to overcome these resistances, okay, which are significant at when we are going on a grade. So now the way this requirement is matched to the gearbox is that, like, we would engage the first gear when we are going on this grade. Okay. So let us recall what we derived as the output of the powertrain in the previous class. We are going to use that expression. Okay. So let the engine provide a maximum torque of Te max. Okay. So considering that the vehicle climbs the grade with the first gear being engaged, we obtain the following. So if you recall the expression for F from yesterday's class, let me go up. So if you recall, we derived this expression, right. So at any engine torque and any chosen gear, this is the expression for F considering the inertia. of the powertrain components. Now imagine that like the vehicle is going at a constant speed on the grade. So the vehicle acceleration is close to 0. So what do you think happens to the second set of terms on the right hand side of this equation? They will vanish, right, because A is almost 0. So what are we going to get? So the tractive force will be equal to the maximum engine torque multiplied by the corresponding gear ratio multiplied by the transmission efficiency divided by the tire radius, okay, so or the wheel radius, right. So that is what we are going to get. So we obtain F to be equal to TE max, NTD I am splitting as NT times ND, NT1 being the gear ratio of the first gear, right. Then we have the transmission efficiency divided by the wheel radius. This has to be matched with this requirement. This is the requirement from the vehicle, right, isn't it? So this is the output from the powertrain when we are operating at a point where we are getting the maximum torque, okay. So if we are getting the maximum torque as TE max and we have engaged the first gear, so TE max times NT1 times ND times eta T divided by RW is the corresponding output from the powertrain, okay, that force output from the powertrain. That is going to be matched to what is required by the vehicle. What is required by the vehicle? It is W sin theta S max plus FR W. So this is one equation that we have. So let us call this as equation 1. Okay. So we can see that we have matched what the powertrain would provide when engaged in the first gear and the engine is operated at its maximum torque point, right, to what is required by the vehicle when it is climbing on a grade. This is the expectation, that is how we are matching both the things, right. Okay. Now in this expression, if you look at this equation, what are all the unknowns here right now? Right now if you look at this expression, there are two unknowns, right, because all the parameters on the right hand side would be given to us. T max is known, transmission efficiency and RW are known. So we need to find NT1 and ND, okay, but we have only one equation till now, right. So we are not yet done, okay. So we are going to see how do we go further on and address this issue, okay. So, but this is the first equation, this is the starting point. Now we are going to get one more equation from the specification of maximum speed, okay. Gradeability is one requirement where we are going to engage the first gear. Now when my vehicle is going at the maximum speed, which is the gear which I would typically engage? Imagine that I start my car from rest, I keep on upshifting from the first gear to the second and so on. When I reach the maximum speed, right, I would obviously engage the nth gear or the highest gear. So that is the other extreme. So the maximum gear, maximum speed choice will give me an equation that would essentially involve the nth gear ratio. So that is an exercise which we are going to do now. So what is that expression? Before we derive that expression, let me introduce this concept of what is called as wheel slip ratio, okay. We are going to come back to this in more detail when we essentially do braking, but for traction the wheel slip ratio or what is called as a wheel longitudinal slip ratio during traction, that is when the powertrain is driving the vehicle, okay, is given by, it is defined as So, different people will use different symbols for this wheel slip ratio, small I, small s, lambda, kappa and so on. Okay. There are different symbols, we are going to choose lambda. Okay. During traction it is defined as Rw times omega w, which is essentially the tangential speed of the wheel r times omega, right, minus the vehicle longitudinal speed v divided by Rw omega w, okay, where v is the vehicle longitudinal speed. Hence, from this expression we obtain that the vehicle longitudinal speed is going to be equal to Rw omega w times 1 minus lambda. That means that if the vehicle is rotating at an angular speed of omega w, the wheel is rotating at an angular speed of omega w at a with the slip ratio being lambda, okay, at the tire rod interface, then the corresponding longitudinal speed is given to be this. Now, what is this lambda? Essentially, if you consider a typical pneumatic tire, which is used in a road vehicle, that deforms, and if you look at the contact between the tire and the road, you have a contact patch or a contact area. When the tire goes into that, it deforms, it sticks to the road and the later part slips and the vehicle essentially is propelled. So, it is not a free rolling motion, okay, there is a slip which is happening at the tire rod interface, and this parameter lambda essentially quantifies that slip. So, we can immediately see that lambda is equal to 0 for a purely rolling wheel, right. If the wheel is exhibiting a pure roll motion, what is lambda? It's 0. Now, what do you think is lambda is for what is called as a spinning wheel? That means, like, imagine that a driven wheel is caught in a pothole full of mud and you press the accelerator pedal, like the wheel keeps on spinning but the vehicle hardly moves, right. So, what happens? This lambda tends to almost 1. So, that is why during traction the definition of lambda is chosen in this manner, so that the value of lambda remains between 0 and 1, okay. That is the motivation behind the choice, okay. So, that is the slip ratio. We will also come back to this when we are dealing with braking, and we will see how it is defined during braking and what is its impact and so on, okay. So, I will stop here. So, in the next class we will come back and continue from here. We will look at the maximum speed specification, how that gives us an equation for the highest gear, and then we also need to figure out, we will also reason out some mechanism by which we determine the intermediate gear ratios, okay. So, that is something which we will complete in the next class. Thank you.